Well, hello and welcome to AP Calculus. We're going to get the ball rolling today by looking at some important and common types of functions. And the functions that you studied in the past have primarily been part of a class of functions called polynomial. And polynomial functions are functions in which we start with a certain power of x to the 11th, let's say, and the powers go down from there. So it might be some number x to the 10th, some number x to the 8th, plus, who knows, down to 9, okay? And a polynomial function, as our definition up here indicates, is a collection of terms added or subtracted together in which the powers are whole numbers. So power 11, power 10, power 9, etc., etc., etc. So some of the functions you've studied in the past have been a 0-degree polynomial, which is a constant function, a first-degree polynomial, which is a line, second-degree polynomial, which is a quadratic. But as I indicated, we can keep going with this, power 3, power 4, power 5. And even though the shapes change as the power increases, there is one thing that stays the same, and that is that your function is always a smooth, continuous curve. A polynomial function will always start at the extreme high or low on the left and end at the extreme high or low on the right. So for example, a third degree, a common typical shape for that is to start down low, does 2 bumps, and up it comes. Fourth degree often starts up at the top, does a couple of dips, and goes back. So the thing I want you to understand at this point, and really the main thing and the only thing I want you to understand at this point, is that a polynomial function is continuous everywhere, it's a smooth connected curve, and its domain is the set of real numbers. Another class of functions that will be important in this course are rational functions. And rational functions are made up by taking two polynomial functions and dividing them. So it's a polynomial function divided by a polynomial function with the condition, of course, that our denominator can't be 0. And because the denominator can't be 0, this causes rational functions to look quite different depending on what the equation looks like. In my first example, I know that x can't be 3. And if you were to graph this function, what you would find is that we get a vertical asymptote at x equals 3. And then my graph looks like so and so. So it actually has a horizontal asymptote along the x-axis. If I change the function just a little bit to become x over x minus 3, again, x can't be 3. And if I bring this graph up on the calculator, I will get a vertical asymptote at x equals 3. And I will also get a horizontal asymptote at y equals 1. And if you look at the graph on your calculator, you will also notice that it crosses the x-axis at x equals 0. So the graph looks something like that. So my third example, I have a different function again. And in this one, you might notice that the top of the fraction can be factored. And that leaves me with a reduction to x plus 2. So you might say to yourself, does that mean that this rational function is actually a linear function? Well, that's partly true, except that the condition is that because we can't divide by 0, x can't be 2. So at x equals 2, there would actually be a hole in the graph. Alright. Now I'm running through these all quite quickly, and the point is not for you to have a thorough understanding of rational functions. That's going to come through the course. What I want you to understand is that when we start dealing with rational functions, a number of problems start coming up. We start getting disconnected curves. We have asymptotes, we have holes, we have a whole lot of other issues that we need to be wary of. Another important classification of functions are piecewise functions, which are functions defined by multiple subfunctions. So in this example, I have 3 functions with restricted domains that make up one sort of master function. So to begin with, I have y equals x squared, which we know on its own is a parabola opening up. But the little piece over here is saying, no, I only want to graph this function, or this part of the function, when x is greater than 0. So if x were 0 here, y would be 0, so that would be right at the origin. But I don't want to include that point because I don't have an equal sign on my inequality. So that's going to be an open circle. And then any value of x greater than 0, which is to the right of the graph, I would graph my regular parabola. So it's going to look something like so. Okay, my middle function is y equals 2, but this is only in effect when x is 0. So that basically becomes the point 0, 2 on the graph. Alright, so I can put that in this spot right here. And then the third branch of the function is y equals 2 minus x, which is a line with a y-intercept of 2 and a slope of -1. So if I graph this third branch, less than 0 for x, because that's the restricted domain, I'm going to start at a y-intercept of 2, which you'll notice is already taken up by that other point I've graphed, and a negative slope, which is going to work backwards to look something like that. And that's my piecewise function. It's a function because each x has only one y, but it's made up of 3 subfunctions. Now, speaking of piecewise functions, the absolute value function is, by definition, a piecewise function. Just to recall that the absolute value of a number is the number itself if this number is positive, and if this number is negative, the absolute value is the negative of this negative number. In other words, the output of an absolute value is always positive. Alright? So with that idea in mind, you know from Math 11 that the absolute value of x is defined to be x as long as x is a positive number, or 0. And the absolute value of x is defined to be the opposite of this x if this x is negative. And that's where my piecewise function definition of absolute value comes from. And then again, you can think of the graph of an absolute value function. A lot of you will immediately think of a V shape for absolute value, but you can think of it as 2 lines, one with a positive slope of 1, one with a negative slope of a slope of -1 going this way, pieced off at x equals 0, greater than and less than that. Finally, just a note on creating new functions from old. We can take basic functions and we can do any of these 5 things to them in order to create more complex functions. For example, in Math 11, you took a basic parabola and you applied transformations to it. So you would slide it, reflect it, stretch it in order to create a more complex graph. So you might remember you could take x squared and you could turn it into something like this, which was a parabola that had been shifted 1 unit to the right, 3 units up, and vertically stretched 2 units. Okay, so through transformations we can take actually any function and create something more complex. We can also add, subtract, multiply, and divide to create more complex functions. So if I were to take the 2 functions shown here and add them together, a parabola plus a line would create a more complex second-degree polynomial function. If I were to take the 2 functions and, let's say, divide them, this polynomial function divided by this polynomial function, I've now created myself a rational function which likely has asymptotes and or holes in it. Now there is one other way to create new functions from old, and that is through what we call the composition of a function, and that's putting one function inside another function. And you read this statement as f of g of x. Alright, let me demonstrate what's happening here with these 2 functions. If I were to ask you to find f of g of 2, what I would do is I would start off with 2, okay, which is my x value, and then I'm going to g that function. And so the output is going to be g of x. So if I take 2 and substitute it into the g function, I get 4. And now, so g of 2 is 4. And now we're going to take the output of that first operation and put that output as the input into f in order to get f of g of x. So when I do that, when I put 4 into f of x, I get 16. If I do this in general, if I take x, so I'm now doing f of g of x. If I put x into g of x, I know that I get x plus 2. And if I then put x plus 2 into f, put this into here, I get x plus 2 squared. And when you do the composition of a function in general, obviously that makes it easier to calculate the value of any particular value of x. So if I wanted to check my first calculation, f of g of 2, which got me 16, I could simply plug 2 into this function. 2 plus 2 is 4, squared is indeed 16.